Look up at the night sky, and somewhere among those distant points of light is a world that has fascinated humanity for centuries. Mars. Today, it is a frozen, barren desert, swept by toxic dust storms, baked by radiation, and stripped of the thick atmosphere needed to support life as we know it. Temperatures can plunge to nearly 140 degrees below 0 Celsius. The air is barely there, less than 1% of Earth's atmospheric pressure. It seems utterly lifeless, almost impossibly hostile. But here is the thing that makes Mars so extraordinary, so endlessly compelling. It was not always this way. Billions of years ago, this same world may have had rivers carving through its valleys, lakes shimmering beneath an ancient sun, and perhaps even oceans stretching across its northern plains. So what happened? How did a planet that once looked so remarkably like Earth transform into the desolate, frozen world we see today? That is exactly what we are here to uncover. To understand how Mars became what it is today, we need to go back roughly 4.5 billion years to the chaotic birth of our solar system. Both Mars and Earth formed from the same swirling cloud of gas, dust, and rocky debris that surrounded our young sun. They were built from the same primordial material, shaped by the same violent collisions and gravitational forces that sculpted the entire inner solar system. In those earliest chapters, the two planets were not so different. Mars, though smaller, likely had a thick atmosphere, volcanic activity pumping gases into the sky, and surface temperatures that could have allowed liquid water to exist. Scientists believe that during the first few 100 million years, early Mars and early Earth may have shared surprisingly similar conditions, warm enough, wet enough, and chemically complex enough that life, had it emerged on one, might just as easily have taken hold on the other. Picture Mars not as the rust-colored wasteland we know today, but as a vibrant world carved by rushing rivers and filled with sprawling lakes. Billions of years ago, ancient Mars may have harbored vast oceans covering significant portions of its northern lowlands, potentially holding more water than the Arctic Ocean on Earth. Scientists haven't arrived at this remarkable conclusion through imagination alone. The evidence is written directly into the Martian landscape and its rocks. Orbital cameras have photographed ancient valley networks and river deltas, unmistakably shaped by flowing water over millions of years. Rovers have discovered sedimentary rock layers, the kind that only form through prolonged water deposition. Mineralogical analysis has revealed clay minerals and sulfates, compounds that require liquid water to form. NASA's Mars Reconnaissance Orbiter detected phyllosilicates, minerals that develop through sustained water-rock interaction across geological timescales. Together, these geological and mineralogical clues paint an undeniable portrait of a planet that once held the fundamental ingredient for life as we know it. Now, what made early Mars capable of holding on to all that liquid water and a thick atmosphere? The answer lies beneath the planet's surface, a global magnetic field. Much like Earth today, ancient Mars generated a powerful magnetosphere, created by the churning motion of molten iron within its core. This invisible shield acted as a planetary force field, deflecting the relentless bombardment of charged particles streaming from the sun. Without it, an atmosphere simply cannot survive long-term exposure to solar radiation. Earth's magnetic field does exactly this job right now, wrapping our planet in a protective bubble that preserves our breathable air and moderate climate. Scientists have found ancient magnetized rocks on Mars that serve as fossilized evidence of this long-lost magnetic field. These magnetic signatures, locked into Martian crust billions of years ago, confirm that Mars once had this critical protection. The presence or absence of a magnetic field, it turns out, can mean the difference between a living world and a dead one. Around 4 billion years ago, something catastrophic happened deep inside Mars. The planet's interior began cooling faster than Earth's, causing its molten iron core to solidify and slow. This gradual shutdown had one devastating consequence. Mars lost its global magnetic field. Without that invisible protective shield, the planet was suddenly naked against one of the solar system's most relentless forces, the solar wind. This is not a gentle breeze. The solar wind is a continuous, high-energy stream of charged particles blasting outward from the sun at hundreds of kilometers per second every single second across billions of years. On Earth, our magnetic field deflects this particle bombardment, sending it harmlessly around our planet. Mars no longer had that luxury. Once the magnetic field faded, the solar wind began doing something slow but irreversible. It started methodically stripping away the Martian atmosphere, molecule by molecule, across vast geological timescales, setting off a chain reaction that would permanently transform the planet. To understand exactly how fast Mars was losing its atmosphere, NASA launched the MAVEN mission, which stands for Mars Atmosphere and Volatile Evolution, in November 2013. MAVEN arrived at Mars in September 2014, becoming the first spacecraft specifically designed to study the upper Martian atmosphere and its interaction with solar wind. MAVEN carried 8 scientific instruments capable of measuring the rate at which solar wind strips atmospheric particles directly into space. The data it collected was groundbreaking. Scientists discovered that Mars loses roughly 100 grams of atmosphere every single second. During ancient solar storms, that rate increased dramatically, sometimes by a factor of 10 or even 20 times. MAVEN confirmed that over billions of years, solar wind has systematically dismantled the Martian atmosphere, reducing its pressure to less than 1% of Earth's current atmospheric pressure. This slow, relentless stripping process fundamentally transformed everything about Mars, setting the stage for catastrophic consequences that would follow. With its protective magnetic field gone and solar wind steadily stripping away gases, Mars faced a devastating chain reaction that would permanently transform its surface. As the atmosphere thinned, atmospheric pressure dropped dramatically. On Earth, our thick atmosphere maintains enough pressure to keep liquid water stable at the surface. But on Mars, something catastrophic began happening. Water's boiling point is directly tied to atmospheric pressure. As that pressure fell, liquid water became increasingly volatile, either evaporating rapidly or freezing solid rather than flowing freely. Think of it like opening a pressurized container. Once that pressure releases, everything changes instantly. The Martian atmosphere eventually thinned to roughly 1% of Earth's current atmospheric pressure. At those levels, liquid water simply cannot exist stably on the surface. Any water exposed to the Martian environment would simultaneously boil and freeze in a process called sublimation, skipping the liquid phase entirely. Those once flowing rivers and ancient lakes were now facing impossible conditions, marking the beginning of Mars's transformation into the frozen desert we recognize today. So where did all that ancient Martian water actually go? Scientists have traced 2 primary fates, and both are equally fascinating. The first path led upward. As the atmosphere thinned and weakened, water vapor rose into the upper atmosphere where ultraviolet radiation from the sun broke apart water molecules into hydrogen and oxygen. Without a magnetic field to protect them, these lightweight hydrogen atoms were swept away by solar wind, lost to space forever. Mars essentially bled its water into the cosmos, molecule by molecule, over millions of years. The second path led downward. A significant portion of Mars's water didn't escape into space but instead migrated deep underground, where plummeting temperatures caused it to freeze solid. Today, scientists believe substantial ice deposits remain locked beneath the Martian surface, essentially a frozen reservoir of that ancient world. Radar instruments orbiting Mars have confirmed these underground ice layers, suggesting Mars holds far more water than its barren surface would ever suggest. So what exactly are we dealing with when we talk about modern Mars? The answer is blunt. It is one of the most unforgiving places in the entire solar system. Start with gravity. Mars has only about 38% of Earth's gravitational pull. That might sound appealing at first, but prolonged exposure to such low gravity would slowly deteriorate human muscle and bone in ways we are still working to fully understand. Then there is the temperature. On a warm Martian summer day near the equator, temperatures might briefly reach around 20 degrees Celsius. But nights can plunge to negative 125 degrees Celsius. The average surface temperature sits around negative 60 degrees Celsius. And then come the dust storms. These are not ordinary storms. They can grow to engulf the entire planet, lasting for months at a time, blocking sunlight and grinding exploration to a halt. Mars does not simply challenge survival, it actively resists it. Despite these brutal conditions, humanity has not given up on Mars. In February 2021, NASA's Perseverance rover touched down on the Martian surface, carrying with it one of the most ambitious scientific missions ever launched. Its primary goal is to search for signs of ancient microbial life, not life as it exists today, but traces of organisms that may have thrived billions of years ago when Mars was warmer and wetter. To maximize the chances of discovery, scientists carefully selected Jezero crater as the landing site. This ancient depression, stretching roughly 45 kilometers across, was once a lake fed by river channels that carved visible deltas into its rim. Dried lake beds like Jezero are scientifically invaluable because fine sediments deposited by water tend to trap and preserve organic molecules, chemical signatures, and even microscopic fossil structures over enormous timescales. Perseverance is methodically collecting rock cores from these ancient sediments, samples that may one day be returned to Earth for detailed laboratory analysis. While Mars may be geologically quieter today, its surface tells the story of an extraordinarily active volcanic past. Nothing captures this better than Olympus Mons, the tallest volcano in the entire solar system. Rising approximately 22 kilometers above the Martian surface, it stands nearly 2.5 times taller than Mount Everest. Its base stretches roughly 600 kilometers across, meaning if you stood at its edge, the summit would actually lie beyond the horizon. You could drive across it without even realizing you were climbing a volcano. What does this colossal structure tell us? Because Mars lacks tectonic plate movement, its crust stayed fixed over a single volcanic hotspot for billions of years. Instead of spreading volcanic activity across a moving plate like Earth does, Mars just kept piling material onto one spot, building Olympus Mons into something almost incomprehensibly massive. It is a direct window into Mars's long and dramatic geological history. And if Olympus Mons represents Mars at its most towering, then Valles Marineris represents the planet at its most torn apart. This colossal canyon system stretches roughly 4,000 kilometers across the Martian surface, nearly the width of the entire North American continent. In places, it plunges 10 kilometers deep and spans 600 kilometers wide, making Earth's Grand Canyon look like a modest scratch by comparison. So how did this geological scar form? The leading theory suggests that Valles Marineris didn't carve itself through water erosion the way most canyons on Earth do. Instead, scientists believe it formed primarily through tectonic stretching and rifting as the Martian crust pulled apart under enormous internal stress, likely connected to the massive volcanic activity building Tharsis nearby. Magma movement underground caused the surface to crack, collapse, and fracture over billions of years. What Valles Marineris ultimately reveals is that Mars was once geologically violent, driven by powerful internal forces reshaping everything above. With Valles Marineris revealing the raw geological power that once shaped Mars, it becomes clear why this planet captivates scientists and visionaries alike. Mars is not just a relic of the past. It represents humanity's most compelling destination for the future. No other world in our solar system comes close to matching Mars as a candidate for human exploration beyond the moon. It has a day nearly identical in length to Earth's, a surface with solid ground, and resources like water ice that future missions could potentially use. Space agencies like NASA and the European Space Agency, alongside private companies like SpaceX, are actively developing plans to send humans to Mars within the coming decades. The motivations run deep, from answering whether life ever existed beyond Earth, to understanding planetary evolution, and ultimately testing whether humanity can become a multi-planetary species. Mars is not just a scientific target. It is a mirror, a mystery, and perhaps one day, a second home. Yet the dream of sending humans to Mars comes with staggering challenges that cannot be understated. Mars has no breathable air. Its atmosphere is composed of roughly 95% carbon dioxide, meaning astronauts would require sophisticated life support systems constantly generating oxygen just to survive each day. Water, while present as underground ice, would need to be extracted and purified using technology we are still developing. Growing food on a planet with poor soil chemistry, extreme cold, and limited sunlight presents another enormous hurdle requiring pressurized greenhouses and advanced agricultural systems. Then there is radiation. Without a global magnetic field or a thick protective atmosphere, Mars receives brutal levels of cosmic and solar radiation that would significantly increase cancer risk over time. Every moment on the surface demands shielding solutions that current technology has not yet perfected. These are not minor inconveniences. They represent fundamental survival requirements that engineers, scientists, and mission planners must solve before any human can safely call Mars home. From a world that once held flowing rivers and ancient oceans to the frozen, barren desert it is today, Mars has taken one of the most dramatic journeys in our solar system. We have traced how the loss of its magnetic field set off a chain reaction that stripped away its atmosphere, erased its liquid water, and transformed a potentially habitable world into the harsh environment we study from millions of miles away. Yet despite everything working against it, Mars remains our greatest destination. Its towering volcanoes, vast canyons, and hidden ice deposits tell a story still waiting to be fully understood. The Perseverance rover is writing new chapters of that story right now, and human boots on Martian soil may not be far behind. The Red Planet is calling, and humanity is finally answering. If you want to stay updated on every step of this incredible journey, subscribe to the channel and check out our latest video. The adventure is just beginning.